In this video, we'll look at salts that contain both an acid and a base. We'll also look at finding the equilibrium constant when we have a mixture of acids, and we'll look at the pH of very dilute solutions of acids or bases. Okay, so let's take a look at this salt solution. Here we have NH4F. This is a soluble salt, so it'll dissolve into these species. Will these affect the pH? And will the solution be acidic, basic, or neutral? Okay, so first determine the major species, and then write the reactions for this one. So this is going to be NH4 plus, F minus, and water. We can write the reactions of these species. So NH4 plus, that's a weak acid, so we'll get NH3 plus H plus. And F minus is a weak base, so we'll get HF plus OH minus. And so what we need to do is determine whether one of these reactions will dominate over the other. So we have NH4 plus and F minus. To do that, we'll look at this table. So there's our NH4 plus and our Ka of 5.6 times 10 to the negative 10. If we look at F minus, and we want to see how good of a base it is, we have to find its Kb. So if we take 10 to the minus 14th divided by 7.2 times 10 to the minus 4th, the Ka, we get the Kb is equal to 1.39 times 10 to the negative 11th. And since this Ka is bigger than this Kb, that means NH4 is a stronger weak acid than F minus is a weak base. That means that the acid will dominate and the solution overall will be at least slightly acidic. Okay, we can also look at what we do if we have a mixture of acids and how we'd calculate the K for the reaction. So in this case, here we have an equilibrium of some ions and we want to know the K value. So if we break this down, you can see we have two reactions here. This HCO3 going to make the CO3 2 minus, and if we see we also have the HPO4 2 minus going to make H2PO4, and we remember from equilibrium we can combine these, so we have the Ka, because this is the acid dissociation written forward for HCO3, and then 1 over the K of HPO4 because this is the acid reaction going backwards. Notice this does not equal to Kb. We're not making any OH minus over here, so this is not the same as the base dissociation. This is just the acid dissociation written backwards. The H pluses will cancel from both sides, and that gives us this reaction that we have written up above. So to find the K, we saw that in general, the K is going to be the Ka of the reactant acid. So in this case, this was the reactant acid over the Ka of the product acid. There's our product acid in this reaction. So we find those numbers on the table and plug them in, and for this equilibrium, we get 7.7 times 10 to the negative 4th. You'll notice in this case, this is telling us that this reaction is going to be reactant favored because this is less than 1. So that means between these two species, we expect the equilibrium to favor this side, which means that H2PO4 is better at giving up a proton than HCO3 minus. And that's consistent with the fact that H2PO4 having a higher Ka is a stronger acid. Okay, so the next thing we'll talk about is the pH, or just how to deal with dilute solutions in general. So here we have a solution of HCl. Its concentration is 10 to the minus 2 molar. And I'll just go through these ones quickly. You can think about the pH of the solution. Okay, and so in this case, it's going to be 2, right? So HCl is just going to go to HCl, going to H plus Cl minus. This is a strong acid, so the concentration of H plus is equal to 10 to the negative 2. And if we do the negative log of 10 to the negative 2, this is just equal to 2. So you can see that in the coefficient here, and knowing that HCl is a strong acid. Okay, but if the concentration is 10 to the minus 4th molar, exact same math, we get the negative log of 10 to the minus 4th, and that's equal to 4. Okay, so this one really quick, 10 to the minus 6th, yep, you guessed it, it's just going to be 6. Okay, so one more, this one, HCl, 10 to the minus 11th, And the answer is no, it's not 11. It's actually none of these. So this one is a little bit of a trick. So if we have the concentration of HCl is 10 to the minus 11th, why, unlike the other ones, is the pH not equal to 11? Well, let's think about this for a second. Okay, so here we have this calculation and this common mistake that we see. So this is the concentration of the acid. And normally we do the pH as the negative log of H+, would plug this in, get 11. But does this really make sense? pH of 11 is going to be a very basic solution, but HCl is an acid. It's also a strong acid, right? So it should never, ever, ever make a basic solution. So what's going on here? Okay, so if we list the major species in this solution, we have HCl is going to dissolve to H plus Cl minus, but we also have water here because this is an aqueous solution. And remember that water, while it's a really low concentration and we usually ignore it, does naturally have some H plus ions. So generally speaking, if the concentration of the acid that you're dissolving, strong acid or strong base, is close to 10 to the minus 7th, so something like 10 to the minus 7th, 10 to the minus 8th, or anything smaller than that, you can't ignore the concentration in water. So in this case, for the actual pH, we'd add these two together. So 1 times 10 to the negative 7th, let's see what that would look like. That'd be 0.0. So that would be 1, 2, 3, 4, 5, 6, 7. And 1 times 10 to the negative 11th, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we add these together and we get 1.0001 times 10 to the negative 7th, which is basically 1 times 10 to the negative 7th, which means that this solution is pretty much still just going to be neutral because it's such a dilute solution of hydrochloric acid. So whenever you see one of these strong species dissolved in water, if the concentration is really low, the solution is still just going to be neutral.